Okay, solving by factoring. So today we're going to move on and actually start to solve quadratic equations. All this factoring review, today you get to see why that was so important. Uh, First of all, let's just remind ourselves about something real quick here. So if I want to solve an equation, we know a graphical trick for this, right? We could graph whatever's on the left side of the equation and graph whatever's on the right side of the equation and look for the intersection, and that works, right? If I do that, look what happens. Okay, so the red graph is the graph of y equals x squared plus 5x. The blue graph is y equals 36. So I graphed the left side and the right side separately. And if I look at the points of intersection, the x values are -9 and 4. So those are my solutions to that equation. Either x equals -9 or x equals 4. Okay? Give me 1 to 5. Does that make sense? Okay, that works. That's a great trick. Okay, what might be a little bit better in general, though, would be to do one algebra step first. It would be to set this equal to 0. So move everything to one side, and the right side of the equation would be set equal to 0. And then what we end up with is a quadratic equation, in this case in standard form. It doesn't have to be quadratic, though. This would work for other types of equations also. Okay, let's see what happens when we look at the graph of the function that we get when we set it equal to 0. Yes? I am recording. Yeah, thank you. Oh, thank you for checking, though. I appreciate it. Okay, so look what happens if I just graph that function. That's the green function, right? The green function is the function y equals x squared plus 5x minus 36. Now, where do you think I could go on this graph to get my solutions of -9 and +4? What do you mean by 0? I heard 0. The x-axis, yeah, right? I'm really doing the same thing. I'm just asking, when does the green graph, the graph of that trinomial, equal the graph of y equals 0, which is the x-axis, right? And sure enough, if I look at the x-intercepts, they are -9 and +4, okay? So that is something that we're going to take great advantage of in math from this point forward, okay? So we know that in general, solutions to a quadratic equation are the points at which the function intersects then the x-axis, right? Okay, if I set a quadratic equation into standard form, the function that's being set equal to 0, I'm really just looking for the zeros of that function, the x-intercepts, right? The solutions could also be referred to as zeros or roots or x-intercepts. For now, those are all going to be essentially interchangeable words. Later on, we will be able to distinguish them. There are some subtle differences. It's nuanced, but for now, just treat them all as being the same, okay? What would, if I'm looking at the graph of a quadratic equation now, if I'm putting a quadratic equation into standard form and I graph the function that's being set equal to 0, what could you tell me has to be happening if there are two solutions? What is the graph of a quadratic function look like? Okay, I'm seeing this parabola, right? Tell me, how would I have to graph that parabola if I'm going to get two solutions to my quadratic equation? What has to be happening there? Go ahead, say it again, Lily. How many times? Twice, right? The parabola must intersect the x-axis twice, which means that if it's opening up, what could you tell me about the location of the vertex? It's got to be negative, right? Meaning the y-coordinate's got to be negative. The vertex would have to be below the x-axis if it opens up, and if it opens down, the vertex would have to be above the x-axis, right? So here's an example, like if I looked at one that's opening up, It'd have to look something like that, wouldn't it? Where now I've got two intersections there and there, right? Okay, what if I get only one solution? What's that going to look like? No, if it's a quadratic equation, so it's a parabola, how could I get only a single solution? What do you think? Yes, sir. Ah, okay. If it just only touches the x-axis once, the vertex is on the x-axis. So something like maybe that, right? And then there would be my x-intercept, right? And how could I have no solutions, no real solutions? Never touches the x-axis. So something like that, for example. Okay. So this gives us a very valuable tool. Real solutions always correspond to x-intercepts. Now, non-real solutions, you might be wondering, what the heck is a non-real solution? We'll learn about that real soon. There are non-real solutions, solutions that are not real numbers. Non-real solutions don't have to correspond to x-intercepts, but real solutions always correspond to x-intercepts. And so as long as we can find x-intercepts, we can find real solutions, which makes technology hugely valuable to us because graphing technology can find x-intercepts pretty easily. You graph a function and look where it crosses the x-axis, right? So that's something that's just hugely valuable to people that actually use math. The disadvantage is if we do something like this, if we're going to use technology to solve an equation, like what about this one? If we want to use a graphing utility to find all the real zeros of that function, well, all I've got to do is just graph the function and look for the x-intercepts. Can anybody tell me what the disadvantage of the technology is? Say it again. They're decimals. Yeah, they're decimal approximations, right? So if the answers were, for example, well, maybe contain square roots or some kind of an irrational number, the technology is never going to give that to me. It's only going to give me back the decimal approximation. But in the real world, oftentimes, that's all we need. It's just an accurate enough decimal approximation. So very useful, okay? All right, but now the question is, how could we solve an equation algebraically? Now we're not going to rely on technology this time. Any suggestions how I could go about maybe solving that equation? What do you think? Okay, so what am I going to do? Okay, or the 13x on the other side? Okay, and take out an x. Okay, so that's pretty good. That's a great way to do it. Any other suggestions? And anybody see anything that might look a little bit easier? It's a great idea. What's that? Okay, what if we divided by x, right? Because we're just trying to isolate x, aren't we? So if I divide by x, then that's going to allow me to cancel an x, and I'll cancel one of the x's there, and I get the answer x equals 13, right? We'll check it, see if it works. Does that plug that back in? Does it work? It does, doesn't it? 13 squared equals 13 times 13. Check. It works. We good? No. Something's wrong. What's wrong, Jimmy? Okay, but you didn't seem happy with that, though. Anybody else unhappy with that? Because you're right. There's something wrong with that. We solved that, and it told us there's one solution. Does anybody see another solution? No, negative 13 is not a solution because I get negative 13 squared equals 13 times negative 13. That would give me positive 169 equals negative 169, which is that's not true. So that's not a solution, but there is one. You do. Can anybody see what the other solution is? 0, right? Doesn't 0 work? Isn't 0 squared equal to 13 times 0? Right? Everybody good? Right? So we made a mistake. Okay, here's the mistake. When solving an equation, you can never divide both sides by a variable because we lose solutions. We lost the solution 0. So our solution was incorrect. It was not complete, right? Now, what Lillian was suggesting was a good idea. I mean, that's what we're going to end up doing, okay? So we need to find a better way where we don't lose solutions. I want you guys, we need to warm up a little bit though. Obviously, it seems like we're a little sluggish here. So let's do a little mental warm up. I want you to do this in your head and just keep track, okay? And you ought to be able to do this. I think you should be able to do this. We're old enough now. You guys are advanced enough math students. You should be able to do this mental math and get the right answer. I expect you to, okay? All right, 2 times 3 in your head. Okay, you don't have to say it out loud, just do it in your head. Now take that, multiply by 5. Okay. Okay, multiply by 3.14159 in your head.
Okay, you lost me.
No, don't give up. You got to come on. You got to be able to get this. I expect you guys to get this right. Okay, take that result and multiply by that number.
Oh my goodness.
Okay. All right. Well, one more. Multiply by that decimal. Okay. All right. I'm expecting right answers. I'm serious.
Yeah, same.
Oh, okay. There we go. All right. Okay.
You lost me at pi. You lost me at pi. I knew. Yeah.
Okay, so the moral of the story is it's a valuable lesson we just learned. The only way that I can multiply factors together and get an answer of 0 is what? To multiply by 0, right? So this gives us something called the zero product property, which is very important. This is kind of a wordy version of the zero product property. Let's rewrite it here a little bit. If A times B times C equals 0, then what has to be true? Yeah, then either A equals 0 or B equals 0 or C equals 0. Those are the only ways it can happen, right? Okay. All right, so then if we want to go about solving something like x squared equals 13x, we're going to maybe have to take a little different approach. Let's do what Lillian was suggesting. If I subtract the 13x to this side, I get x squared minus 13x equals 0, okay? So far, that doesn't do me a lot of good having that equal to 0 because this is not written as a product of factors. Right now, finding values of x that are going to make this equation true is kind of tricky, right? We probably could reason through this one because it's not that complicated, but in most cases, we can't. In most cases, it would be difficult or impossible to find the values of x that are going to make all those terms add and subtract to 0. Hopeless quest. But what could we do? What could I do? But how am I going to do that? I want to use that zero product property. What could I do? I could factor it, couldn't I? Okay, what could I do to factor that? Okay, I could undistribute an x, right? If I undistribute an x, what am I left with? Okay. Okay, so then the only way that this product of two factors, I have a blue factor times a green factor, right? The only way the product of those factors can equal 0 is how? If one of the factors is equal to 0, right? Well, what are the possible things that could happen then? What are the possible values that would make that work? Well, one of them is if the blue factor is equal to 0, which means x is 0, right? The other possibility would be if the green factor is equal to 0. And when does that happen? When x is 13. There you go. So those are my two solutions, x equals 0 or x equals 13, right? How do we get it? By factoring and applying the zero product property, okay? So in general, to solve by factoring, there really are just 3 steps. We're going to put the equation into standard form, which means setting it equal to 0. We're going to factor the expression, and then we're going to apply the zero product property. Okay, does this always work? No, not always, because sometimes things don't factor, right? Sometimes we could have an expression that's prime that doesn't factor, and then this technique wouldn't work, and we'd have to move on to plan B, which we haven't learned yet. But when this works, it's super easy. Quick and easy way to solve an equation, okay? Let's try a couple here. What about this guy? What would I do? Yeah, I've got to factor out a GCF. Good. So if we do that, let me scoot this over here a little bit. There we go. Okay, so my GCF is what? 5x. Okay, and then what am I left with? No. 81, there you go. Okay, good. Could I go further? Good, I could break that apart again, couldn't I? So we've got our 5x. And then let's break this up into a blue factor and something else. So what's that going to factor into? Okay, we'll do purple. What about the blue one though? So x squared minus 81 factors into what? X minus 9 times x plus 9, right? And so now we've got 3 factors, right? We just need to find the zeros of each of those factors. Those will be my 3 solutions. So what's the zero of the first factor? In other words, when I say the zero of the first factor, what I mean is the value of x that makes that factor equals 0, right? 0. Okay, so one solution is x equals 0. What's the solution to the blue factor? 9. Or x equals 9. Or, whoops. There we go, right? Okay, making sense? Okay. Don't make the mistake, there's a common mistake. Don't make the mistake when you factor of assuming that the magic numbers are the solutions. They're not, right? The magic numbers are not the solutions. You get the solutions when you set the factors equal to 0. Okay? How about this guy? What am I going to do? Okay, good. I got to set it equal to 0. Which side should I definitely move everything to? Deegan, how come? You're right. You're correct. Well, I'll move it to the left. Why? Good. We want a to be positive. We want the coefficient of x squared to always be positive. The leading coefficient needs to be positive. Whatever the biggest power of x is, we need to make that one positive. So we're going to scoot everything over that way. And that's going to give us what? 3x squared. Oh, and I'm going to make a change here too. I messed this one up. This is supposed to be a minus. Yeah, change that on your notes. I mean, it's not, if you're writing this down. If you're not writing it down, don't worry about it. Okay, so what was this next one? Minus, what's the next one going to be? No. Okay, after 3x squared, what's next?
Wouldn't it just be just 1x squared? Because it's x squared minus. Wouldn't it be plus 3?
Oh, yeah. You're right. Okay, you know what? So this one does work. Never mind. It does work. Okay, you're right. It is x squared. Yeah, never mind. This is x squared. I'm thinking about the next example. X squared minus 17x, right? Okay. And then that should be a minus 72. Yep, that needs to be minus 72. Because otherwise it's not going to work. I can see that. Sorry. I'm waffling here, aren't I?
A little bit, yeah.
There we go. X squared minus, well, finally we'll get this right. Minus, my goodness, minus 17x plus 72. That's going to work. Equals 0. Okay. Gosh, that was hard, huh? So now, what am I going to do? Regroup a little bit.
GCF.
Yeah. Is there a GCF? No. Okay, but we got to try, don't we? We got to try.
Now we go up.
Okay. Okay, so we got to try to factor this, right? Are there magic numbers that multiply to positive 72 and add to negative 17? What is it? Negative 9 and negative 8.
There we go.
Okay, so then what are my solutions? X equals 9 or X equals 8. Again, don't make the mistake because the magic numbers were negative, right? The solutions are positive, right? Okay. Yes, always the opposite. Yep. Okay, how about this guy? That looks ugly, huh? But don't now we don't panic when we see equations that have fractions in them. What do? We clear the fractions, don't we? Yeah. What can I do? What can I do to clear the fractions here? What am I going to multiply by? 6. So when I distribute the 6 to the first term, what do I get? Z squared. Okay, so distribute to the second one, I'm going to get minus 15z. And to the third one,
36 times 6 is 126.
no, how about 216?
I'm so close. Oh my gosh, the exit number just let me finish.
Okay, so now we've got to factor this thing, right? Okay, so does it factor? So now think about the signs. What are the signs going to be? If it multiplies to negative 216 and adds to plus and minus and adds to negative 15, which is bigger, the negative or the positive? The negative. So let's put the negative first. We always want to put the biggest one first. Negative and a positive. And remember what I told you yesterday too. Normally, when we're trying to find magic numbers, we would find factors of the constant that add to the linear coefficient, right? Factors of negative 216 that add to negative 15. That's a little tricky. It's not terrible, but it's a little tricky. It's easier though when we have opposite signs for our magic numbers. Don't find factors. Instead, just find groups of numbers that add to B. It's way easier. So we want to find numbers that add to what? To negative 15, where the negative one is the biggest, right? And they have to multiply to negative 216. But we're just going to find a list of all those numbers. So somebody throw out the negative number. Somebody throw out a 22. Okay, let's try 22. Negative 22, and then negative 22 plus what is negative 15? 7. Okay, so if I multiply those together, I'm going to get negative 154. Okay, so that's not right. I need bigger stuff. What is it? Okay, there we go. So let's move down the list. We need bigger numbers. Let's scoot down to negative 24 and 9. And what do you know? That gives us negative 216. Okay, good. Right? So then if our magic numbers are negative 24 and positive 9, what are the solutions going to be?
24 and negative 9.
Z equals 24, or, that's not a very good or Z equals negative 9. There it is. Okay. Yes. Well, it's Friday. Right? Okay. Okay, we're almost there. We are almost there. A couple more and we're done. Move everything to the left because we want positive value of A, right? Okay, so if I move everything to the left, I'm going to get positive 8x squared plus 65x minus 63 equals 0. Yikes. Okay, we got to factor it. Can I factor out a GCF? Can't, right? Okay, so this is one where we're going to have to factor by grouping, right? We're not going to use slip and slide. We'll factor by grouping. So what do the numbers have to multiply to? They have to multiply to 8 times negative 63, right? So that's going to be 504, negative 504, right? So multiply to, what do they have to add to? 65, okay? What are the signs going to be? Positive and negative, right? So, right, the positive is bigger and there's the negative. So this is another example where we could use, we could find numbers whose sum is 65 and see if some of those have a product of negative 504. Start us off, somebody. We need a big positive number, small negative number. This might be close. What is it? Well, they have to, the positive one has to be bigger. Well, it's got to be bigger than 65, right? Say it again. 79. Want to try that one? 79 plus what is 65? Or sorry, yeah. Negative 14. Everybody agree? Those add to 65. Okay, so that's gonna be way too big, isn't it? Way too big. So we need smaller numbers, right? It's gonna have to be a little bigger than that. Should we try like, I don't know, like 72? 72 and what? There we go. Okay, and that's it, isn't it? Okay, right. So we got our magic numbers. So now what are we going to have to do? We have to factor by grouping. So what are we doing? Our magic numbers are 72 and negative 7. So I split the 65x, right? We're going to split the middle term. This guy is going to split. Which one should we do first? No, we should do the negative one first, right? So we're going to split it into minus 7x plus 72x. And the others stay the same. And now what? Okay, GCF of group 1 is what? X. Okay, so we factor out an x, and we're left with what? X minus 7. 8x minus 7. Okay, good. Plus, how about group 2? What can you tell me about group 2? 9. Okay, but before we even write that down, what do we know has to be true? The binomial has to be the same. 8x minus 7. So that means what goes out front? Either way, it's still 9. It's 9, yeah. Okay, good. So now what? No, I'm not done.
You combine 8x minus 7 and then you factor that out.
I'm factoring that out. That's what I wanted, right? I'm going to undistribute the green factor. So we undistribute the 8x minus 7, leaving us what behind? X plus 9. Yeah. Okay, so We're there. The red one's easy. What's the red solution? Okay, the green solution, we could set 8x minus 7 equal to 0, right? And then just solve. But you guys, you can do that. You can kind of solve it. You can solve it in your head a little bit. If I want to solve for x, what am I going to do? I'm going to have to add the 7 to the other side, right? Which is going to make it positive 7, and then divide by 8. See? Good? I did. Yeah. Okay, give me 1 to 5. How we doing? Okay, all right. What do we got here? Okay, now this one looks really tough, doesn't it? It's way easier than the last one. Way easier. We don't want to multiply. That's going to make a mess. Remember, okay, somebody raise your hand and help me out with a strategy here. What's going on? Sophia, help me out with a strategy. You know what's going on. I guarantee you got this figured out. What am I going to do? I don't want to multiply those together, right? I want to factor it even more, right? Does that make sense? Because my goal is to write this as a product of factors. If I multiply those out, I'm undoing the work that's already been done for me. That's already been factored into 2 factors, right? So I just need to break these apart. So what about this first one? This will be our blue one. What's that going to break into? What are my magic numbers going to be? 5 and 3. X plus 5, X plus 3. Okay, these will be the red. -4, +3. Okay, so what are my solutions then?
-3, +4, and negative. I can't see the last number.
We already have that one anyway, right? So I get 3 solutions, -5, -3, and 4. Good? Piece of cake. Okay, let's call her a week. What do you say?
Yes.
Okay.